In this video, we're going to be looking at an application of the standard molar enthalpy of chemical reactions formula. Specifically, we're going to calculate the mass of a specific fuel that we would need in order to generate a specific amount of power. Now, this question can be solved either by using the formula from the previous video or Hess's law, but we're going to focus on the former to give you additional practice. In both cases, we need two pieces of information before we can begin. Firstly, we need the standard molar enthalpies of formation of all of the products within the reaction, or product and reactant compounds rather, and then we would need the balanced equation in order to know what we multiply our enthalpies of formation numbers by. I'm going to write out the balancing coefficients now in order to save time, but remember that you'd have to do this yourself under normal circumstances. From here, we need to figure out what our enthalpy of formation values are, and in this case, because we're given the enthalpy of formation of octane, the fuel in the question, and because we used carbon dioxide and water vapor in the previous video, we can write out the enthalpy of formation values here in order to save time. But where do you get these numbers from if they're not given to you in the question? The answer is that you need to look at a data table like this of all of the pertinent thermochemical values in order to find the enthalpy of formation for the compounds in question. You'll have to be careful when using a data table like this because you can see that C8H18 has multiple entries based on the state of matter or what type of isomer you're looking at. But we can see, if we look carefully, liquid octane has the standard molar enthalpy of formation value that matches the one in the question that we were given. If you want to use Hess's law to solve this question, you'll need to break down all of the compounds within the equation into their component elements to make sure that all of them cancel in order to give us the overall reaction. We can quickly do this, but remember the focus of this video is using the standard molar enthalpy of reaction formula here. So we know octane breaks down into 8 carbon and 9 hydrogen gas molecules. We know that carbon dioxide breaks down into 1 carbon atom and oxygen gas, and we know that water vapor breaks down into hydrogen and oxygen gas with the proper balancing coefficients like so. Now at this point, again, you can try doing this calculation using Hess's law and see that it will give you the same thing as the standard molar enthalpy of reaction formula, because that's the one we're going to focus on. So the first thing we'll need to find is the total standard molar enthalpy of formation of all of our product molecules. So because there are 16 carbon dioxide, we're going to do 16 times 393.5, and this is the total standard molar enthalpy of formation of all 16 carbon dioxide molecules, and to that we're going to add 18 times negative 241.8, and this is accounting for all of the water molecules. If we expand both of these numbers out, they come to negative 6,296 and negative 4,352.4. Now, for our reactant molecules, this is significantly less work because we remember that oxygen gas is an element in its standard state, which means that we don't actually need to write anything for its enthalpy of formation because the enthalpy of formation of elements in their standard state is assumed to be 0 because they have effectively always existed. So the only number we need to add is 2 times the standard molar enthalpy of formation of octane here. And again, if we multiply a negative times a negative, it becomes a positive 499.8. And if you put these numbers into your calculator, you'll find that the total standard molar enthalpy of reaction for this reaction comes out to be negative 10,148. Let's fix that. 0.6 kilojoules. Now, you'll note that I've written kilojoules because typically delta H is written in the form of kilojoules per mole of the particular compound we're referring to here. And we know in the fully balanced reaction here, we had 2 molecules, or 2 moles, if we want to use moles here, of octane here. So if we wanted to find the kilojoules per mole, we would need to divide this by 2 moles of C8H18, and this number comes out to 5,074.3 kilojoules per mole of C8H18. Now, normally we would be done, because normally in this type of question, the final answer that we want is expressed in kilojoules per mole. However, in this case, it's an application question, so we're actually wondering how many kilograms of this stuff we actually need in order to generate a specific amount of power. And that specific amount of power that you can see in the opening is 1.0 times 10 to the 11 kilojoules of power, which comes to, I believe, 100 billion kilojoules of power. That's a lot of energy. Now, if we want to figure this out, we need to figure out how many moles of octane we need, but since we have our delta H term here, we can cancel kilojoules by dividing by 1 mole of C8H18, which generates 5,074.3 kilojoules per combustion reaction, and that this would tell us the number of moles of CH18 that we would need. But again, the question didn't ask for moles, it asked for kilograms of octane that are necessary, which means we need to find the molar mass. I'll trust that everyone remembers the molar mass of carbon is 12.01, and there are 8 carbons within this molecule, and then we add to that the molar mass of hydrogen, 1.01 times 18, and if you calculate this, it comes to 114.26 grams per mole is the molar mass of octane. So we would simply need to multiply this molar mass number, 114.26 grams per mole. So we see that moles cancel here, and this tells us the number of grams of octane that we would need, which comes to a very, very, very large number, which is why the question asks for it in kilograms, so we know that 1 kilogram is equal to 1,000 grams. And if we check our units, we see that we are left with kilograms of octane left based on this delta H value. And if you put this into your calculator, and if we keep in mind our final answer has 2 significant digits, your calculator should read 2.3 times 10 to the 6 kilograms of C8H18 that is needed. And that concludes our video series on using enthalpies of formation in order to calculate the standard molar enthalpy of chemical reactions. And now that you have seen how this can be used in applications, you are ready to tackle the practice problems that follow this question here.